focused primarily on understanding the ecology of tropical systems. And as a postdoctoral scholar at UC Berkeley, Emilio is working with John, myself, and Susie to understand the effects of the California drought on dynamics, mortality dynamics, and fuel dynamics, and is sealing his accreditation toward being a global ecologist. Our second speaker will be Leif Mortensen, who's a U.S. Forest Service, who's with the U.S. Forest Service at the Pacific Southwest Research Station, who does a lot of excellent work in forest entomology. So when he's not IDing forest insects or crawling over dead and down trees for field work, you can find him exploring new places, usually using his bike, and conducting an informal and highly secretive inventory of where Pacific yews can be found. So with that, we will kick off with Emilio, then we'll go straight to Leif, and we'll take questions for both speakers after that.
All right, thank you, Jody. I hope everybody can see this okay. All right, I see a thumbs up there. So first of all, thank you for being here today. And before I start, let me also thank all my great colleagues here listed and co-authors of some soon-to-be paper, hopefully published soon also, that have been really helpful in putting this together about understanding ground and surface fuels across Sierra Nevada forests. I am particularly grateful, I want to point this out to Jody Axelson and John Battle for giving me this opportunity to learn more about the forests of California, Sierra Nevada in California. I don't think I'm saying anything new here, but despite the abundance of terms such as catastrophical and destructive, when talking about fires for much of the West, and particularly California, we live in a fire-prone area. And as Stephen Pine mentioned in this book, California burns and frequently conflagrates. The coastal sage and shoreblood burns, the mountain encrusting chaparral burns, and the mountain woodlands burn, and the conifer-clad Sierra Nevada burns. So there is a number here saying that an estimated 54% of California ecosystems are fire dependent, and most of the rest are fire adapted. So fire season, so the saying goes, lasts 13 months. And I think last year proved that fire is a major issue in the state. Indeed, for thousands of years, culturally rich communities across the West understood the importance of fires and had in fire an essential component for their land management activities and culture. So the idea of this slide is to show briefly a distribution of indigenous territories in California, as well as all the potential uses of native plants for which fire is also an important component. But with the eradication of indigenous populations and colonization of Euro-American settlers in the West, began an area of fire suppression, essentially with the idea of protecting forests with favored timber harvest and a growing population. There was a huge effort of suppression. So this slide shows an example of the fire history in one point in California, Blodgett Forest Station. So each horizontal line here is a single tree, where there has been some sampling of the tree rings chronologies, and each vertical line indicates a fire scar. So you see that after a certain period, early in the 20th century, there's a lot of these trees basically lost the signals of fire, so due to fire suppression. And on the right, you see also a big piece of redwood tree where some of the fire scars are starting to spread away after the 1855 around, when most Native Americans were being displaced from their territories. So what are the main effects in the landscape? It is well documented that fire suppression induced densification of many forests. So this photo shows a comparison of the Yosemite Valley in the Yosemite National Park between 1899 and 2011. It's clear that we see more trees and denser forests on the bottom. The figure on the right, it shows a retrospective study that compare this issue between the 1930s and the 2000s. And we see that in the more modern times, you see more trees per hectare or more trees per area. Comparatively, at least from the study, lower basal area, probably as an effect of the decline in big old trees. Jody already pointed out, and Craig and Bill did a great job also highlighting the issue of droughts, but I think it's important to highlight this. So I don't have to remind you that, that between 2012 and 2015, Some people put it all the way to 2016. California had one of the worst or severe droughts ever recorded. One of the particularities of this drought is that it was a combination between higher temperatures and really low precipitation. So Jody mentioned at the beginning that one of the causes is more than 150 million, at least from the aerial detection monitoring conducted by the Forest Service, more than 150 million trees have died, and probably more are dying as we speak. The concentrated to the south of the Sierra Nevada. So this figure, this bar chart just show preliminary results of the basal area of all the 13 locations we're working on right now, and I'll talk more shortly. So you can see the idea of showing here is there is a trend toward an increasing in dead basal area towards the south. So using a figure that I recently saw from a presentation from Park Williams about the 2020 fire season, I wanted to point out the three major points or aspect of what is the current situation of the Sierra Nevada forest. We know that we have dense overstocked forests that are susceptible to bark beetles epidemics, and there is an increase in tree mortality rates. At the same time, warming temperatures and the increasing severity of droughts are causing an increase in the aridity or the facilitated an increase in dryness throughout the landscape. And at the same time, we know from many studies and statistics that there is a higher density of housing and population living in the wetland-urban interface. So it's an increasing probability of ignition for fires. The next speakers later in the morning is gonna also discuss about the fire. So I'm gonna talk about the component of fuels of this triangle. We know that with weather, topography, and vegetation structure, ground fuels, in this case, I'm referring to ground fuels for DOF, and surface fuels are of interest because of this. Fuels are fundamental factors driving fire behavior, severity, and intensity. We know that greater surface fuel loads increase potential surface fire flame lengths and can lead to canopy torching, which means more severe fires. So it's very well known that having accurate estimation of fuel loads can help in the efforts to reduce wildfire risk via having good estimation for prescribed burning, thinning, and other restoration planning and carbon projections. So in this work, basically this is a result of one of the collaborative features of this network. We wanted to address three main questions. So what is the approximate biomass of ground? Again, ground meaning DOF fuels, and surface fuels after the 2012-2015 drought. But I'm highlighting here prior to the commencement of widespread snowfall, so across a range of forest conditions. I'll talk more about that. Also, the other question is, can relatively thin vegetation groups with different fuel load signatures be identified based on the forest structures and composition, and how well this overstory structure and composition and other biophysical variables can explain the variability in surface fuel. So we combined two independent network of forest plots across 13 different locations in the Sierra Nevada. On the left is a map of 9 locations that are managed by UC Berkeley and by the tree mortality collection, the data collection network. We have the lowest number of plots is 22 in one of the sites at Blodgett Forest, and we have 46 in plots in other in Mount Home demonstration forests. On the right, we have a network of 180 plots distributed across 4 national forests with 45 plots per national forest. So in total, we have 462 plots in 13 locations for more than 1,300 fuel transects. And from the overstory standpoint, we have data for more than 10,000 stems or individuals, for which 66% were alive at the moment of our evaluation. So we follow the traditional planar transect method from Brown to measure fuels at 3 transects per plot. Fuels were classified, as you see in this table, by the time it takes to their internal water content to respond to changes in atmospheric conditions. So we are talking about small fine woody debris, 1 hour, 10 hour, and 100-hour fuels, and 1,000-hour fuels or coarse woody debris are referred to small logs and limbs. And we measure depth of litter and DOF in this plot as well. All this information, the counts and the volumes of logs and the depth of depths and liter were transformed in equivalent of biomass using this great working package developed by Danny Foster from UC Berkeley that has all the equations and coefficients needed to transform quickly all the information that we collect in the field into biomass of fuels, and also gives information about the overstory. This is a very detailed slide that I'm not going to explain in detail, but essentially to answer two questions, we developed this 5-phase analytical approach. The first part is characterize all fuels load by these 13 locations, 3 major regions across the Sierra, North, Central, and South, and 3 elevation classes. And secondly, we start exploring this potential relationship between fuels and overstory and biophysical parameters. Then we use a cluster analysis to see how can we extract potentially distinct vegetation groups. And 2 final connected steps were used to address potential drivers of fuels, including vegetation, overstory, and biophysical variables. So quickly, a few of the results that we found. Please, on the x-axis, we have the fuel load in megagrams per hectare on the biomass of fuels for different fuel classes. The y-axis shows the 13 locations from the north in the Plumas National Forest to the south in the Sequoia National Forest. The first thing that comes out here is that the highest biomass for liter and duff was found at the Blodgett Forest Ecological Reserve, where essentially no management other than fire suppression was conducted. Cottonwood watershed on the Stanislaus Forest in the Central Sierra had the highest biomass for 1 hour, and coarse woody debris, or 1,000-hour fuels. The highest biomass for 100-hour fuels was in the single tree selection system that has been happening at Blodgett Forest. And overall, Cottonwood and Mount Home had the highest biomass of large fuels or coarse woody debris, largely influenced by the presence of several big logs in some of the plots. When we classify all the plots in 3 major elevational groups, seen here in this color, for 3 major classes of fuels, in this case, duff, fine woody debris and liter were grouped together, and then coarse woody debris or 1,000-hour fuels. The only major difference that we found was on the 1,000-hour fuels, where high elevation plots had a much higher load, essentially driven by the presence of large logs. Otherwise,
1 minute, Emilio.
Okay. We found 4 distinct vegetations using the K-means cluster analysis. One is dominated by incense cedar, Douglas fir, and ponderosa pine. It has the highest density of live trees and the lowest density of basal area. The second cluster is mostly dominated by firs, white and red firs, and to a lesser extent by ponderosa pine, and it had the second highest density of live trees. The cluster 3 is the one with the lowest number of plots. It's dominated by giant sequoia, and it, as expected, had the highest live basal area and stand density index. And finally, we have this larger cluster dominated by ponderosa pine, incense cedars, and black oak, and it has the highest density of dead trees. So the major signals here for this in terms of fuels is that cluster 1, dominated by cedar, Douglas fir, and ponderosa pine, has 60% of fuels, basically dominated by liter and duff. The second cluster, the fir-dominated cluster, is 60% dominated by coarse woody debris. As expected, the giant sequoia one is dominated by coarse woody debris as well. And the ponderosa pine cluster, the last one, is where liter and duff had the highest biomass among the 4 clusters.
That's time, Emilio, if you could wrap up.
Yes, I'm going to wrap up in the next slide. So essentially what we found here when we tried to analyze the potential of biophysical and overstory parameters to explain the amount of fuel is that basal area and tree density were positively correlated with duff, while slope was negatively correlated with duff, but on a relatively low explanatory power. For fine woody debris in liter, we found that, again, total vessel area, and in this case, SDI, were positively correlated. And with a very low planetary power that cannot tell us much about the 1,000-hour field, we found that QMD, or quadratic mean diameter, and elevation were positively correlated with the abundance of coarse woody debris. So finally, we found high levels of fuels, mostly with values closer to the pre-treatment that have been found in other studies, reflecting that most of the plots have been lacking a recent fire treatment. We have these two potential extremes of fuels, one where Segi or giant sequoia have the largest coarse woody debris, and on the low end, ponderosa pine dominated cluster. It's really hard, as you may see, to have good interpretation of what are the potential predictors of fuels using overstoring biophysical variables, especially because fuels are especially clumped on multiple scales, but we hope that this information can help informing models of fire behavior and other components. Thank you. Sorry for going forward.
Great, thanks so much. It's a lot to ask our speakers to present science results in 10 minutes. So we do appreciate the attempts and me butting in. Great talk, and we will have a Q&A after this. So Emilio, if you'd like to share your screen, we will.
I think it's Leif's turn to share his